always, sometimes, never. Now we want to determine if we have three vectors, x, y, and z, all of the same size, is it the case, always, sometimes, or never the case, that the dot product of x with the quantity y plus z is equal to the dot product of x with y plus the dot product of x with z. You'll notice by problem 1.4.3.6 and 1.4.3.7, I think, that this is at least sometimes true. It gives me an indication that it might be always true, so let's try to prove it. If we run into some trouble, we might want to go back and see if we can find counterexamples, that is, three vectors where this is not the case. But let's see if we can prove it for now. So my proof is going to be just as usual, starting with letting x, y, and z be vectors that are arbitrary. Arbitrary. Sorry about that. And then we'll start with one side of the equation and show it's equal to the other. And in this case, I'm going to again start with the left-hand side. We have the dot product of x with the quantity y plus z. Now, what does this mean? It means first we need to do the vector addition, take the result, which is going to be a vector of size n, and then do the dot product of x with that result. So, in order to get a handle on what this is, what I'm going to do is use notation to describe the components of the vectors. And x will be the vector with components chi sub 0, chi sub 1, and so forth, chi sub n minus 1 if it's of size n. Y will write as the vector psi sub 0, psi sub 1, and so forth, psi sub n minus 1. And z will write as the vector with components zeta sub 0, zeta sub 1, and so forth, zeta sub n minus 1. And now we need to first look at the vector sum. So what we'll have here is the dot product of x with the resultant of summing y plus z, which is going to be the vector of size n, whose first component is going to be psi sub 0 plus zeta sub 0. Next component will be psi sub 1 plus zeta sub 1. And its last component will be psi sub n minus 1 plus zeta sub n minus 1. This is by just vector addition. So now we have two vectors of size n that we're going to take the dot product of. And you'll recall that dot product, the result is a scalar that is found by adding the product of corresponding components in the vectors together. So what we would do is we would, for each one of the components, I'll call that this I from 0 to n minus 1, we will take the component in x, we'll call chi sub I, and multiply it by the corresponding component in the result of our sum, which would be psi sub I plus zeta sub I. But again, these are just real numbers. And what do we know about real numbers? Well, one thing we know is that multiplication distributes over addition on real numbers. So this means that what we have is equal to the sum from 0 to n minus 1 of the chi i's times the psi i's plus the chi i's times the zeta i's. But again, this just means to add up some real numbers. And the real numbers that we're adding up are created by taking a sum of real numbers. We know that real number addition has other properties. It's commutative and it's associative. So the order in which we do our addition doesn't make a difference. So because real number addition is commutative and associative, we know that this sum is equivalent to the sum from I equals 0 to n minus 1 of the chi i's psi i's plus the sum I equals 0 to n minus 1 of the chi i's times the zeta i's. Now let's look and see what we have here. This first term is just the dot product of x with y. And the second term here is just the dot product of x with z. By definition of dot product. So what do we know? We know that when we started with x transpose times the quantity y plus z, we ended up with this always equaling the dot product of x with y plus x with z. It's always true. We could describe this as dot product distributes over vector addition. So I'm going to write that out. Dot product distributes over vector addition. This is a very important theorem.